So, hello everyone. Welcome to Quantum Spacetime Seminar. Today we are very happy to have Petr Kravchuk from King's College London, and he's going to tell us about higher twist operators in CFT. Over to you, Petr.
Thank you very much for the introduction and the invitation to give the talk. Yes, today I'm going to be talking about this kind of idea of higher twist operators in CFTs and then explain what I mean by this. This is based mostly on work in progress, so it's not, apologize me if it's like not too precise in places, and please do ask a lot of questions. This is a work in progress mainly with Jeremy Mann, but I'll also mention some results from work with Brett Orlto and Johan Henriksen, which is also work in progress, so similar caveats apply. So let me start with some motivation. The basic idea is that, like in many talks about conformal field theories, to try to understand the spectrum of conformal field theories which are as general as we can. So non-perturbative, non-supersymmetric, doesn't matter. And among this kind of ideas, like for this goal, perhaps one of the most powerful ideas that we have is this idea of light cone bootstrap. And kind of the main statement of light cone bootstrap is that you have two primary operators in a conformal field theory, like O1 and O2. And say O1 has the scalar dimension delta 1 and spin J1. The O2 has delta 2 and J2. And then we can form this sort of so-called double twist operators, which will denote O1, O2, brackets, subscript J. So this is the primary operator of spin J, and often you can also see another subscript N, and I'm just taking here N equals 0. And the idea behind this is that these operators are in some sense well defined if this subscript J, the spin of this operator, is much larger than the sum of the constituent spins. And the key property of this operator is that can be constructed from O1 and O2, and it will have the twist, which is the scaling dimension minus the spin, which is approximately the sum of the twists of the constituent operators. And the corrections here are going to be suppressed by powers of J of spin. So because this twists add, we call them double twist operators. And this little n that I had here, if you don't set it to 0, then you're going to set plus 2n here, in addition to tau 1 and tau 2. And this is kind of a powerful structural idea about the spectrum of the CFT. It tells you that at least at large spin, there is some kind of additivity in the spectrum. You can take kind of simple operators and construct more complicated operators out of them. So maybe you take O1 and O2 and you construct this kind of operators, but then you can start taking these operators and combining them with, for example, again, O2, construct more complicated operators. So the basic intuition behind this, there are kind of few ways of looking at this sort of double twist operators. So one kind of the most intuitive way, I think, is to think about this holographically from the point of view of idea space. In which case you imagine that O1, let's say if you take O1, the operator O1 on its own, and look at the corresponding dual state in the ADS, then perhaps it's going to be some kind of excitation, which is hopefully going to be localized in some region. Maybe this region will be large, or the ADS radius, something like that, but it's somewhat localized. And then if you have two, O2, it's also going to be some localized excitation. Then you can put them very far apart and make them spin around each other like this. And in this language, the spin of this kind of combined state is related to the distance between them. The distance is approximately logarithm of the radius. Sorry, distance is approximately logarithm of the spin. And so, you know, if there were no interactions, then the energies of the states would just add. But when we do have interactions, we expect some sort of potentials which are going to be decaying as, for example, exponentially, if you have some massive exchange particles between these two blobs, and then you're going to have the energies of the states add, and you're going to get some parallel corrections after you plug in this logarithmic and spin distance into this potential. So this is kind of very sketchy idea, but it sort of works. But then there are other ways of looking at this. And the most common way, or maybe the original way, is that we view the states as arising from the crossing equation for 4-point functions. So we can view a 4-point function with 2 insertions of O1, 2 insertions of O2. We can expand it in different channels. And then you look at the particular limit, which is not going to be important for this talk. But the idea is that in this limit, in one channel, you have exchange of operators of low twist, which is, you should think about as related to this massive exchange particles. And you find that in order to reproduce these contributions in another channel, in cross channel, you need to insert here some sequence of operators. And these operators are precisely these double twist operators. And if a more modern approach to this is the Lorentz inversion formula, which again is not going to be super important for this talk, but the rough idea is that the Lorentz inversion formula gives you properties of various operators as an integral, some integral expression, 4-point function. And then when you take the limit of large spin, you can approximate this 4-point function by contributions again of some low twist conformal blocks. And once you plug this low twist conformal blocks into this integral, you get again the prediction that these double twist operators should exist. And kind of the most naive, perhaps, way of looking at these operators is just think about what happens in free theory. So let's say maybe you have a free theory which has a fundamental field phi, let's say free scalar. Then you can certainly build operators which look like this. You can take phi, and add a bunch of derivatives. You build this composite operator. It's going to have twist exactly as exactly 2 tau phi. And so this is what you would call this phi double twist in this case. So this prediction is very easy to verify in free theory.
So, Petr, one question.
Yeah.
Are there operators in CFT with large spin which are not of this type?
That's a good question. That's actually exactly what I'm going to come to.
Okay.
I'm not going to be able to answer it completely, but yeah, that's the question. So you can even ask, are all operators double twist operators? And by double twist operators, we have to mean not just taking some fundamental field and doing double twists, but also we should allow first things like we take maybe here we have phi and we do double twist of phi, but then we start adding maybe phi, another sort of double twist, and then you can add phi, this sort of combinations. And then we can ask, can we get all operators in this way?
Okay. But you also want to say some large spin you want to bring in that condition, or even without
that? So I want to ask this question without this condition, and exactly yes. I guess what you're driving at is that then you can complain like what do I mean by that? Because I just said that these operators are at large spin. So you need to consider large spin to even talk about this operator. So what can I possibly mean by saying that, or are all operators double twist operators? In this sense, indeed, and this is not a well-defined question, and maybe it is well-defined, but the answer is obviously no, because while take any spin 3 operator, it doesn't quite look like a double twist because 3 is not a very large number. But then you can refine it a little bit, and you can ask about Regge trajectories. So, well, maybe even before we think about Regge trajectories, you can still ask the question about double twist operators, even without thinking about Regge trajectories in this form, as long as you can sort of unambiguously assign to like an operator to a trajectory. Say if you have a part of spectrum which looks sort of like this, you say this is what happens more or less in 3D Ising model, that if you make a plot of lowest dimension operator at every even spin, and then you compare this to twice delta sigma plus j, you'll see that there is a bunch of operators which live very closely to this line. And then you can be pretty confident to say that all of them are part of this family. But of course, if your situation is more complicated and you have a bunch more operators here, then it's much less clear which particular operators have to be understood as lying in this trajectory, if any. But then you can sort of try to refine this question using the idea of Regge trajectories. So expect that at large spin here, you can look at this line, and then you should see some points approaching closer and closer to this line, and then you can kind of confidently associate these points to this double twist family. But then also we expect that operators in CFTs organize into Regge trajectories, so that there are some analytic curves kind of canonically associated, canonically defined in some sense, analytic curves which pass through local operators. And then we also expect that each double twist family of this kind, if we form these operators, they will all live on a single Regge trajectory. That's the expectation, at least. There's not the proof of it, but as far as I can tell, but that's what you would expect naively. And then you can ask this question in terms of double twist trajectories. You can build Regge trajectories which at large spin are populated by double twist operators. Then you can analytically continue these trajectories to low spin. And then you can ask whether it's true that there is a double twist trajectory passing through every operator. And this is something that I think can be true. I'm not going to be able to prove it, but I think it can be true. And we can see this happening in some examples. So here's a plot with from some paper that we are preparing with Brett and Jochen. So this is, in this picture, we have twist 4 operators in Z2 Wilson-Fisher theory, in other words, using model in 4 minus epsilon expansion. And in this plot, you can see orange. So this is at one loop. So what? Let me explain what this is. The vertical axis is anomalous dimension, or you can think about this as basically twist shifted by some number. Horizontal axis is spin. Orange points are just the local operators. They're twists of local operators. So for example, it's spin 2, there's just one twist 4 operator. Twist 4 just means that the twist is close to 4. So if you take this number here, multiply it by epsilon, and add 4, this is the physical twist. And to get these orange points, what you do is you just kind of, list the operators in phi to the free scalar theory, turn on phi to the 4 interaction, compute the anomalous dimensions. You get some matrix that you diagonalize, and then you get this kind of mass of points. But then you can also ask what are the Regge trajectories, and then I'm not going to go into details, but you can write non-local operators, Leiter operators, you can renormalize them, and then you can also diagonalize some dilatation operator acting on the Leiter operators, and then you'll get these curves. So this gray region is just a region where our diagonalization procedure doesn't work, so this just means that I cannot tell you what happens inside here. But other than that, you can see that we can see, like we don't make any assumptions, granted, except that we're studying a perturbative theory at one loop. We don't make any assumptions, we just compute the Regge trajectory separately, local operators separately. And we see that we have, through each local operator that we could find, except those in this gray region, you see that there are some Regge trajectory passing, and if you kind of keep going to the right, you can actually track how this particular Regge trajectory becomes a given double twist trajectory. So, and this is kind of a lot of operators, and as you go further to the right, their number is growing and growing. And this is an untrivial example where you can see that this seems to be true, that even though these operators, let's say, built out of 4 fields, phi, you can still track them down to some double twist trajectories of lower final operators, even down to low spin. But this picture also, sorry, yeah.
But just one question. So, for general theories, maybe you said it on the previous slide. For general non-perturbative theories, is there a way to define Regge trajectories? How does one define Regge trajectories? Or is it a notion that makes sense perturbatively at large A or something?
So, kind of the simplest way to define them is through inversion formula. You can, well, I mean, so when you say define them, you can define them in the simplest way in the following sense. For example, inversion formula gives you this function C delta J, which so it allows you to compute it at non-integer spin, and this function has poles at positions of local operators. So if J is integer, then the poles in this function are going to be the positions of local operators. And then if you set J to be non-integer, well, we don't actually know, like, to be like the complete honest answer is we don't know what happens to this function when J is non-integer. We know that it's analytic in delta in some region, but we don't know what its singularities are. If you assume that that it remains meromorphic as it is for integer spin, then the positions of the poles are going to be the quantum numbers of Regge trajectories. But this is not proven. Perturbatively, what you can do is you can actually, to each point on a Regge trajectory, associate, also non-perturbative, that's what we expect to happen, that to each point on a Regge trajectory, associate a non-local Leiter operator. And then one thing that you can do perturbatively is you can just write down expressions for the Leiter operators in some ways you write down expressions for local operators. And then you can renormalize them, turn on perturbations, find divergences, subtract them, compute anomalous dimensions, and this will give you these curves.
I see. Okay.
So the perturbation theory, you can see that this is true, that it is meromorphic, but you cannot, I don't know how to prove it in non-perturbative theory.
I see. And these curves can cross in perturbation theory?
So there's not a theorem that they cannot cross. I mean, generically they shouldn't cross. You know, we say that there is no level crossing in quantum mechanics, but this just means that level crossing is non-generic. So here there is a similar statement that crossing of Regge trajectories is non-generic, but you cannot prove that it doesn't happen because, of course, if there's some, imagine there is some integrability kind of symmetry that you didn't know about, then it would allow them to cross, even though you didn't know about the symmetry, right?
I see. Okay.
So, for example, without knowing about n equals 4 integrability, one might be surprised that some trajectories cross there, but they cross because some subtle quantum numbers are different and they're allowed to cross. But here, for example, actually, it's a good question maybe because here you kind of didn't look into details near this point. It would seem that these two trajectories cross, but if you zoom in, you can see that they actually barely avoid crossing here.
Yeah, sorry, this is what I wanted to ask. So what does this mean that they avoid crossing? You mean actual analytic functions avoid crossing? Where are these green points coming from in near 6.2 and so on?
Yeah, so this is, maybe I should have explained this in more detail. So the way these curves are obtained, these curves, is that we write down expressions for perturbative Leiter operators in this theory. So in free theory, all these curves would be on top of each other and it will be just straight line at 0 because there would be no anomalous dimensions. Then we go to one loop and we do renormalization and we get some trivial dilatation operator which acts on these Leiter operators. So unlike with local operators, at every spin there is an infinite dimensional space of Leiter operators. So if you were able to kind of erase this gray region and look what happens underneath, you would actually see that the trajectories accumulate near 1/3. And we diagonalize numerically this kind of dilatation operator. It's an integral operator which acts on this infinite dimensional space of functions. And then we get this trajectory. So for every spin, we kind of cut it like this, and there is a diagonalization problem to solve. And so we solve it. So we can just make plots of the solutions. And that's part of the statement. But we see that the solutions pass through local operators. For every local operator that we see, at least in this group of operators, there is a Regge trajectory which passes through this operator. And then once you have some Regge trajectory, you can kind of keep going to the right and track what happens to these operators as large spin. And you see that they become double twist operators for some combination of basic two operators from which you build them.
I see. No, but just near this point, this 6.2 in the insert here. So there, these curves, when you say that they don't quite cross, it actually comes out of your diagonalization procedure that they don't cross.
Yeah.
I see. Yes, thank you.
And actually, I think this near crossing illustrates one interesting feature, which is also, you can see by analyzing this plot more carefully, but you cannot see it by eye. This thing you can see by eye, which is that, sure, this green trajectory, as I said, if you follow it all the way to the right, eventually it will become a double twist trajectory. But it's not, this observation is not particularly useful if you want to understand, say, this operator here. In the case, if you study, say, the reading Regge trajectory in 3D-izing, as you to even Regge trajectory, say this operator is going to be the stress tensor. It's spin 2, and the light cone bootstrap is actually very well developed to the degree that you can see, you can predict the anomalous dimension of this Regge trajectory from light cone bootstrap, and you can see that the anomalous dimension is such so that the scaling dimension of stress tensor is 3 to like sub% level. You can very precisely calculate the scaling dimension of stress tensor from light cone bootstrap and see that it's indeed what it should be, even though this is just spin 2 and light cone bootstrap is supposed to work at large spin. So you can be hopeful that maybe you can push this further. But this sort of behavior, for example, shows you that this is not possible in general and cannot be possible in general. Because what this near crossing tells you is that if you were actually to go off in the complex spin of J, you would see branch cuts. Because whenever you have an avoided crossing like this, you can go in a complex plane and you can pass from one trajectory to the other through a branch cut. And having a branch cut means that whatever expansion you have from large J, it's not going to work on this side anymore. If anything, it will be giving you this trajectory if you try to just ignore the distance of branch cuts. And so while technically this operator here, for example, is on a double twist trajectory, its properties are like, if you were all powerful, you could maybe predict its properties, but in practice, it's very hard to predict its properties from viewing it as a double twist operator. And the same is actually true for all these operators, or at least for most of them. It's just hard to see here. What happens is that, this Regge trajectory, it might look like it's straight, and probably it's already kind of is at the, at the twist that is predicted by the double twist trajectory, but it's not. So what happens is that you need to go quite a bit to the right to see it transition slowly to the correct twist. So the twists that you see here, even though the trajectories are nearly horizontal, are not the correct asymptotic twists predicted by the double twist bootstrap. Eventually they become so, but not at low spin. And so what I'm just trying to say here in a very convoluted way is that I think what could be true, so the possible answer to the question of whether all operators are on double twist Regge trajectories, is that they could be, and we can see in some examples that they are, but the asymptotics that the light cone bootstrap predicts for these double twist trajectories will, for most operators, receive very large corrections at finite spin. And when I say large corrections, I mean corrections which are not likely to be able to resum from this large spin perturbation theory. And trying to understand these large corrections is what motivates at least me to try thinking about what one might call triple twist operators or quadruple twist operators or higher twist operators in general, more generally. Because in this context, for example, as I said, these are operators of twist 4. So they're built out of 4 phi's with some derivatives inserted. So at large spin, you might extract some symptotics, but at low spin, it might be more useful to look at them as kind of actually remember that they're built out of 4 phi's. And to make this kind of, so let me phrase it slightly differently. Instead of in this holographic setup, instead of trying to think about.
Hi.
Yeah.
Yeah. So you made this statement that on the correct Regge trajectory, these double twist operators might have some distance. This in the page below this correction. The page below this. Can you go to the page below this? Yeah, this tau1 plus tau2 plus this j to the power some correction, there's some power. So can I interpret this in this sense? In the above picture, these straight lines are not the correct trajectory. Since you mentioned that if you go to the very right of the graph, they form the correct trajectory. And the distance of these dots from the appropriate, if you extrapolate those correct trajectory on the right to the back, these distance between these dots, the one which are the operators, is of form this tau1 plus tau2 plus j to the power something.
So, sorry, let me try to make a statement and then we'll see if it answers your question, because I'm not quite sure I understood exactly what you're asking. So let me just state more carefully what I mean here. Let's say we look at this trajectory over here, and I say that this is double twist trajectory of O1 and O2. Then when I look at when I go to the right along this trajectory, I expect the twist to approach, let's say for simplicity that this is twist and just forget about the explicit numbers. I expect the twist to approach tau1 plus tau2. And the approach is going to be governed by power law corrections. So that's the expectation. And then from this picture, because this picture is already kind of approaching some value, it seems, you might guess that tau1 plus tau2 is just this value at which this trajectory sits. In fact, that's not what happens. I mean, for this trajectory, it probably happens pretty quickly. But if you go to kind of these trajectories which are lower here, what happens is that it actually sits at a different value for a while, which is not tau1 plus tau2. And tau1 plus tau2 is, say, here. And the trajectory sits at some other value for a long while. And then eventually, it kind of transitions to another value. And this approach is this j to the minus some power. Whereas this behavior here is not described by this power.
Okay, got it. Thanks.
But it's kind of hard to show in these pictures. Also, this Regge trajectories, I only have them up to 20. Anyway, it's just I would show more plots. It's just that's a bit tricky to show, and I don't want to dwell on this too much. Anyway, my point is that it's possible that there, as I will discuss, that it's possible that there is something to be kind of learned in a similar spirit at large spin, but not from the point of double twist trajectories, even if all operators do sit on these double twist Regge trajectories. And I think a good illustration for this is just think about this problem holographically. So when we had two like double twist trajectories, you just had two body problem, two things flying around each other. And then you can imagine a generalization where you have sort of three body problem. And of course, you know, if you're anything like me, you might be scared of three body problems because they can like fly around in very complicated chaotic patterns. But then you could also guess that, if you take operators which look like O1, O2, and then we take double twist as O3, you can predict that in terms of this kind of ADS blobs, it should look like we have two blobs relatively close to each other, which are O1 and O2, and maybe orbiting. And then there is a kind of a blob far away, which is O3, which orbits these two. And we have some sort of orbit like this. And this is what the light-cone bootstrap can predict for us, properties of states like this, when everything is far apart, but O1 and O2 are kind of close enough to each other so that when we consider their interaction with O3, we can forget about them, the details of this state, and just treat it as one operator here, and then just reapply our light-cone logic to this large system. So that's the sort of states you can expect to make sense from the light-cone perspective. On the other hand, you could also guess that if you just look at generic configuration, say 3 states, these 3 blobs far apart, you might worry about stability of these configurations, but maybe it's possible to have configuration where they're all just sort of the same distance from each other, say equilateral triangle and orbiting like that. And it's still at large distance. So it's still something you might be able to predict, but not necessarily from using these iterated arguments, because this sort of states would be far away from the states of the light-cone bootstrap type. And so you can ask, is it possible? And viewing this from, so that's kind of my main motivation to ask if this is possible. And before I go there, I just want to discuss a little bit this kind of say triple twist states from various perspectives. So from the holographic perspective, it's kind of the most straightforward one and intuitive one, but also maybe a bit scary, which is that it would require us to think about 3-body problem in ADS. Then on the CFT side, trying to generalize this 4-point crossing argument, you would imagine that maybe you try to reproduce some contributions in one channel by inside of a 6-point function by this kind of triple twist contributions in another channel, just generalizing this picture here. And so people are working on this sort of idea. I'm not an expert on where they exactly are right now with this, but it's something that's being discussed, and it's not really what I'm going to focus on, but you could imagine some strategy like this could work. So in free theories,
one question.
Sorry. Yeah.
Sorry, one question. It's a bit tangential, but I think related. So can one understand what exactly these blobs are? Blobs. So can we talk about an operator which corresponds to a blob which does not have any internal orbiting structure? Some sort of a indecomposable unit. And just try to characterize those.
Well, that would be just trying to, I guess in this picture, if you just have an operator,
any finite spin operator,
some finite spin operator, then you would just say it's a blob.
Yeah.
And unless it is in some sense nice and has large spin, and then it might be actually constructed of several other blobs.
Okay.
And I don't know how seriously one should take this blobs picture for, say, double twist operators. For me, the kind of the solid foundation for these double twist operators is in terms of, say, crossing equations, inversion formula.
Okay.
But that's certainly a good intuition, and I kind of in the rest of the talk, I'm actually only going to be talking about this sort of pictures and not about these crossing equations. So I just wanted to mention that you could imagine trying to understand these more complicated things in this more rigorous way, but by studying, say, 6-point functions and light-cone bootstrap for 6-point functions, people are trying to do this. It's not what I'm going to talk about. But also, another thing I wanted to say is that if you just want to understand them, say, in free theory, and if you understand them in free theory, you can add perturbations. then it's also easy. It's just as easy as double twist operators, as you can build operators of 2 fields. You can build operators of 3 fields. There's a bunch of derivatives between them. That's not a problem. So the problem becomes when we add interactions, and that's going to be the main subject of the rest of the talk.
I have a question.
Yeah.
Like for the 3-point function, three operators going to 3 operators, how do you kind of do the crossing relation? Because, I mean, how do you kind of construct the S-channel diagram corresponding to this T-channel diagram?
I mean, I think the answer is I don't know. So I don't know, and it's I think this is an open problem. People have been, as I said, making progress on various kind of limits of this, but the results that I'm familiar with are more like trying to get results about this sort of objects from 6-point function, rather than this sort of democratic configurations that I'm hoping for.
I see. Okay.
Yeah, and there, when you try to do something like this, I guess the intuition for what to do here is, in some sense, you're just trying to embed this idea inside of itself. So you're taking some repeated limits, which are kind of similar to what happens in 4-point functions. But as I said, I'm not really an expert on this approach here. Right. And maybe actually also highlighting some difficulties that you can see in this approach is that another comment I wanted to make is, when you focus on double twist case, this a little bit obscures the problem. Because, say, if you want to understand it in this language, in the holographic language, in principle, what you need to do, you start with your conformal field theory, and then you need to understand, in some sense, this some sort of effective interaction between these blobs. And then you solve your 2-body problem, 3-body problem, and then you get anomalous dimensions from there. Now, when we're talking about the double twist operators, you need to solve a 2-body problem. And 2-body problem is kind of trivial. And because of that, anywhere you look in kind of like bootstrap literature, nobody bothers to tell you this, in some sense, effective interaction. And the result is always immediately the anomalous dimension. Because once you know kind of the potential, you know what the energies in the 2-body problem are. And that's not so easy anymore if you try to understand, say, 3-body problem, because if you have these 3 blobs, first question is how they interact, but even if you know how they interact, it's still a 3-body problem, and you need to solve that. Kind of in a more down-to-earth language, if you try to, say, just take a free theory, you have triple twist operators and add some interactions, like 5^4 interactions, then the idea is that once you think about this fields, say, built out of 3 phi's, then at a given spin, there is a large degeneracy, because you can distribute the derivatives between different fields in different ways while keeping the spin and scaling dimension fixed. And so you're going to have some dilatation operator on a highly degenerate subspace that you're not going to need to diagonalize. So there are 2 steps. You first need to understand what this operator is, and that involves doing Feynman diagrams with something specific to a CFT. And then once you have this kind of large matrix, you need to still diagonalize it. And in some sense, that kind of this step is analogous to getting the dilatation operator, and then solving the 3-body problem is analogous to just diagonalizing this large matrix. And another thing that I want to highlight is that when you have a 2-body, like double twist operator, so you just have 2 of these blobs, if you have large spin, this means that these 2 blobs are widely separated. So you can also trust the effective interaction because you can imagine that you have some sort of expansion and at large distance. Now, when you have, say, triple two-stop operators, so you have 3 of these blobs, you cannot trust your approximations just because you have large spin, because large spin means that some distance is large between these 3 blobs, but the other, say maybe O3 is far away, but O1 and O2 can be very close. So you have to, like when deriving this effective interaction, you also have to consider the kind of states you want to evaluate this interaction in. Now, getting to this effective interaction is highly dependent on the CFT. And I think kind of both problems here are hard. And in some sense, if you cannot understand the second problem of trying to do something with this effective interaction, I personally am not very motivated in trying to understand what this interaction is in the first place. So the thing that we try to do is to actually focus on the second step and try to figure out in some kind of model examples, if we have some effective interaction, can we actually understand something useful about the energy levels of the system, about the anomalous dimensions, given this effective interactions between these blobs or this D. So again, of course, in this example with kind of perturbative quantum field theory, it's perturbative, so you can diagonalize this D-infinite dimensional subspace. Our philosophy was more like, is there something that we can say about this problem that would be generalizable and hopefully to kind of general CFTs? So,
sorry, Peter, one question in this context of perturbative theories. I mean, if you think of, so you talked about some sort of a 5-4 type interaction or something, but you could have, let's say, a graviton exchange, and if it is perturbative, then I guess it's clear that you want a Born approximation, right? So if you want a 3-body kind of, I mean, I'm just thinking that there are 2 graviton exchanges. What I was thinking is that you don't quite get a separate 3-body part because everything is happening pairwise.
Well, yes and no, right? You can have pair interactions, you can have 3-body interactions. I'm going to focus on pair interactions, but it's not, I don't think this is a kind of a conceptually significant limitation.
Okay.
Well, for concreteness, I'm actually going to focus on a very simple model, but then I think the way we solve it is very non-specific to this model, and so it wouldn't have to be, you wouldn't have to rely on, like, say, 2-body interactions in general.
Okay.
So again, so I was very vague, I realized, so let me try to be much more concrete. I'm going to focus on a very concrete model so I'll replace these blobs, this kind of ADS blobs, by particles. So in simplicity, I'll just take a massive scalar in ADS. So I have this phi bar. I'll take a charge to just get rid of some mixings. And I'll also add just a real scalar, which is going to act as some sort of massive exchange particle. And again, the fact that this is a scalar is not significant. I could have had gravitons or whatever you like. Just formulas are simpler with the scalar. And so it's going to kind of mediate some interaction between phi and phi by just this cubic vertices. And the reason so in this model, there is some coupling constant, which I'll assume to be small in some sense. And which just means that I'm going to be doing some perturbation theory in this coupling constant. But you shouldn't think about this coupling constant as just because I'm doing this perturbation theory. You shouldn't think about this as being kind of a perturbative setting. What one really should imagine is that if all these kind of blobs are well separated, then the interaction is weak just due to kind of attenuation by distance. And doing perturbation in G here is just a kind of a toy model for this, and I'm just focusing on this toy model because then I can make statements which are precise, and then we can ask how general they are. But within this perturbation theory, in this model at small g, what I'm going to say is going to be precise. So
sorry, I have a question.
Yeah.
Like, what does the one, the dotted one represent? I missed what you said. Can you
here,
please
I haven't said anything about this yet. Sorry.
I see. Okay.
Yeah.
Sorry,
So-
Petr, can you make this point a little bit more precise, that this smallness of G serves as a proxy for large distances? Because
Yeah,
I thought the smallness of G will let you consider pairwise things. On the other hand, if you had large distances, it does not necessarily follow that you can do pairwise interaction. Is this correct?
Yeah, this is correct what you're saying. Well, let me try to give. Let me first comment on this. So one way to view this model is that, say you did a light cone calculation just for the double twist case, where you did this crossing symmetry idea or the inversion formula, where in one channel you included the exchange of the identity operator. So this dotted one is the exchange of the identity operator in the P channel, and also included the exchange of a scalar operator sigma. And asked what does this mean for the anomalous dimension of the double twist operators. So at large spin. So what I say here is not perturbative in any way. You can ask this question in any CFT. I mean, of course, it's perturbative at large spin because I'm assuming here that sigma is like the lowest twist scalar or something of this sort. But the answer to this problem is exactly equal to the leading order in G correction to energy of two particle state in this Hamiltonian. Basically, when I say G small, what I mean is I want to consider exchange diagrams. So kind of two-body exchange diagrams, and that's it. Sorry, not two-body, but like pair exchange diagrams like this. And you can view this as maybe an effective Hamiltonian. But as I said, this is a bit work in progress, so I'm not exactly sure what to do, say, with this higher particle interactions, as you said. So this is why I'm trying to formulate this in this kind of very narrow way. And then we can try to see how general is the answer that we get. Because, for example, in the double twist case, the answer that you get from here is exactly the full, complete, non-perturbative and J answer from the Lorentz inversion formula that you can compute on the CFT side. So in other words, whatever this captures, there's nothing in kind of the usual double twist bootstrap that it doesn't capture. Maybe it doesn't capture everything that there is if you need to consider triple twist operators, but it definitely is good enough to capture everything that we know about the double twist case.
So I have another question. Like, are these lines or propagators on the left-hand side, are they bulk to boundary propagators? Because in order to match with the CFT, that's the way it should have to be, right?
Here?
Yeah, are they bulk to boundary propagators? I mean,
this is maybe I should put it in quotes. This is kind of the this is a conformal block exchange diagrams. This is very schematic. This is supposed to.
I get that. But since you're doing it in ADS,
so here you should think in this expression, you should think about phi as being the boundary scale, the boundary operator derivative.
Yeah. So boundary scalar. So then the propagators would be.
You mean these propagators?
Yeah.
That's what I'm saying. You shouldn't interpret this as a Feynman diagram. Interpret this as a conformal block.
Okay.
I just meant this in the sense of this kind of approach to the double twist operators. So when you follow this approach, you include something on the left-hand side, some exchanges. So here I'm saying if I include 1 and sigma and kind of throw the full power of Litecoin bootstrap at this problem to determine the properties of the double twist operators, I'm going to get some answers. And the answers are going to be exactly the same as the leading order correction in G to the energy of two particle phi state in this ADS model.
So
exactly.
What is for the ADS model? I mean, what is the fundamental difference between considering it in ADS and in flat space?
Because I want to study the CFT, so I'm taking kind of a holographic picture, and CFTs are due to stuff in ADS. So that's why I'm putting things in ADS.
In the CFT, I understand you have this block decomposition thing, but in ADS, what is the analogous thing? That's what I'm confused about. I mean,
well, these blobs are supposed to be in ADS. That's the holographic picture for this states. So I'm just modeling here each blob as a phi particle in ADS, and the interaction is just being mediated by a sigma particle. That's a model. I'm just trying to see how far I can get with this model, and then we can talk about more complicated things or other things. My point is that I think we can learn something from here, which is going to be useful, even if you start complicating things by multi-particle interactions and so on. Maybe another comment about multi-particle interactions. I think multi-particle interactions are going to be, this is not that I'm not 100% sure about it, but I think if you imagine some kind of interactions of this sort, they're going to be suppressed by higher powers of J than the direct two-particle interactions. So, sorry, I'm running a bit late in time, so let me try to move on. So yes, as I said, for double twist case, you can really capture everything that we know about Litecoin bootstrap within this model, and at least at the level of formulas. And for higher twist operators, this of course will only include pair interactions if I go to the linear order in G. Then we can separately discuss how to add higher particle interactions. Now, if G was 0, then we would just have 2 free scalars in ADS, and this is due to mean field theory. So our, say, 3 particle states would be just described by this sort of expressions in this generalized mean field theory. And what's going to happen when we add perturbations is that this sort of subspaces that we had in the MFT, which were degenerate, will break, the degeneracy will be broken, and breaking the degeneracy is some non-trivial diagonalization problem for whatever Hamiltonian interaction Hamiltonian this produces. So first thing to discuss here is the kind of how do you describe states and particle states. And there are 2 ways I want to approaches that I want to mention to this. So one approach is kind of very formal, and this is just getting the answer mathematically. So the statement is that if you have some sort of n particle state, so state containing n pi particles in free theory, then you can completely describe the state if you know this expectation value, this matrix element. So you take vacuum, you act with n pi operators, and you take the inner product of psi. So if you know this is a function of x1 through xn, this completely kind of contains the wave function of this n particle state. And so this function I can use to characterize the states. So if I also require to that psi is a primary state from the point of view of conformal symmetry, parameterized by some embedding space coordinates. I'm not, due to time, going to go into a whole lot of details in this, but the bottom line is that there are some simple general rules which allow you to conclude on the basis of symmetries that if we focus on those states which have the leading twist in free theory, so just have scaling dimension is just the n times the scaling dimension of phi plus the spin. So if you look at the states with leading twist, then their wave functions actually very constrained, relatively speaking, to be some standard prefactor times a polynomial psi in some variables alpha 1 through alpha n, where this offers us some expressions in terms of embedding space coordinates. But the important point is that kind of the functional degree of freedom which exists in these wave functions can be described as a polynomial of degree j, homogeneous polynomial in degree j, in these complex variables alpha 1 through alpha n, and this polynomial has to be shift invariant. So also, if you choose kind of a nice configuration, the way you should think kind of the values this variables alpha I take are complex general complex values within the unit disk. And as I'll explain in a second, we should really think about this unit disk as being kind of a Poincare disk in the sense of the hyperbolic plane. So this is.
Sorry, these things follow from conformal symmetry?
Yeah, this just follows from conformal symmetry.
Okay.
Well, conformal symmetry and some general thinking about what the states can be. It's kind of like thinking how it's more or less the same problem as just trying to think what kind of operators of this sort you can build.
I see.
And this is in some sense depends on some polynomial in this partial derivative. And this actually gets just translated into this polynomial in alphas.
Oh, I see. Okay.
And what I want to highlight is that this is really a formal derivation, but then it's kind of rigorous. There are no holes there. And then I can give an informal derivation, which is completely not rigorous, but gives a bit more physical intuition. So let's consider first one particle in ADS, but also a classical particle. So just a classical particle of mass m is going to have an action like this. And then we're going to parameterize everything in global coordinates. So we have sort of global time, we have some sort of radial distance, and then we have some extra d-1 dimensional sphere, which also have a metric. So and this metric, I'm going to, well, how much time do I have left? I don't remember when we started.
Sorry, Peter, we are not very strict with time, so please take your time.
All right, I don't have
pace.
anything else to do, so I can continue. If you want me to finish, just tell me to finish, okay?
Great, yeah.
So, all right, then let me not try to rush. So I'm going to parameterize EDS in global coordinates. So we have global time, we have rho, we should think of like a radial coordinate in kind of ADS sort of cylindrical coordinates. So rho equals infinity is the ADS boundary. And then we have this kind of the space, the sphere, the SD-1 sphere, which parameterizes various angles. So let me just draw a picture to be more clear. So the global time goes up, rho goes out from the center, CFT sits at the boundary. So this is rho equals infinity. And then even at fixed rho, we have some sort of sphere, and this is our SD-1. And on this SD-1, I'm also going to choose some coordinates which is going to consist of a angle phi and some angle psi and metric on SD minus 3. So there are two ways of thinking about this. So one way is to just compare this line to this line, and you can see that psi is kind of analogous to rho. So it's the same sort of coordinates in some sense. Another way of thinking about this is just to forget about psi and everything else. Just think about d phi squared, and then in this picture, phi is just the kind of the polar angle here. But of course, in higher dimensions, you have more coordinates, and so you need to add the size and everything else. But this is going to go away, so it's not very important. Then an important point is that the way this phi is chosen is that if you shift phi by constant, then this is an isometry. So this is just a rotation of the whole EDS. In particular, it's a rotation in the CFT sense. And the Hamiltonian associated with global time translations is the same as the dilatation operator. So if you make a change of variables where instead of kind of translating in t and keeping phi fixed, you can retranslate in t while keeping this phi tilde fixed, then this new Hamiltonian is going to measure not the scaling dimension, but it's going to measure the twist, the difference between scaling dimension and the eigenvalue of some rotation generator. So let's do this. Let's write our.
Are you considering EDS3 here, or you're just?
No, I'm considering EDS d plus 1. So that's why I have this bunch of angles, which I don't really want to talk about.
No, I mean, in the approximation that you're ignoring those large extra angles, you said that you're just considering phi. So in that approximation, is it some
No, sorry, I'm not making an approximation here. So in this picture, I can only draw phi because I can only draw projections of three-dimensional space. But in principle, in this formula, any ADS will work, ADS 5 or ADS 4, just that you'll have to think about this size. But even like the equations are correct in any ADS, just this picture is an illustration for ADS 3. These are some particular choice of coordinates on this SD minus 1. Important point is just that in any dimension, shifting phi by constant is a rotation. So phi only enters through d phi. It doesn't enter anywhere else. That's the point. Basically, I mean, I can say more about this parameterization. It's if you have a sphere, so this is a two-dimensional sphere. And then, of course, if we well, actually, sorry, let me not go there. It's not going to be very helpful. I'm just going to miss things. Anyway, this is correct in any dimension. And my point is just that if you make this change of variable, then your new Hamiltonian is going to be measuring the twist. That doesn't rely on ADS3. ADS3 is just simpler because you don't need this part. So if you make this change, you're getting this somewhat messy metric. So what happened is that phi is now phi tilde plus t. So you replace d phi here by d phi plus dt. So d phi plus dt squared is going to d phi tilde plus dt squared is going to give you a d phi tilde term, which is the same as this one used to be. It's also going to give you a dt squared term. So this term is going to get modified. And there's going to be a cross term, which is d phi tilde and dt. And then, as I promised, it's not a rigorous derivation, so I'm just going to anticipating that I want to work with low energies in these coordinates. So with low energies, which means low velocity, so I'm just going to expand around this small velocity limit in this section. And so this is sort of like a non-relativistic expansion. And when you're doing non-relativistic expansion, you know that the coefficient in terms of in front of dt becomes your potential. And here, the potential is this coefficient, the kind of gravitational potential. And in terms of psi, it's, it can be written like this, and has a minimum when psi is 0. So you're setting a certain sort of minimum of potential if psi is 0. And of course, you could go away from this minimum, but then you'll get greater energy. And I want minimal energy, so I'm going to set psi to 0. I'm just trying to understand the kind of minimal energy configurations here. In terms of, this is a classical analysis. If you imagine quantizing it, then there is going to be, effective harmonic oscillator for psi, and there is going to be some ground state energy, but I'm just sitting in the ground state.
I'm confused about something like when you're doing this light cone business, when you're twisting the phi to phi plus t or something, aren't you going already to the relativistic limit?
Well, this really depends on, when you say relativistic limits, it really depends on what coordinates, right? Because, for example, I'm here expanding, I'm expanding in phi tilde. And if I'm telling you that phi tilde dot is small, then obviously phi dot is approximately 1, which is ultra relativistic. So in terms of phi, yes, it's ultra relativistic, but in terms of phi tilde, it's not.
I see. Okay.
And again, I don't want you to approach this as an extremely rigorous thing. You'll see that it gives the same answer as the previous discussion of what the Hilbert space is. It just gives a bit more intuition. So,
Petr, one question. The psi equal to 0 is being singled out, although psi equal to any value should be the same, equivalent, right? Psi equal to 0 point is being singled out here, right? As some sort of a minimum of this thing. But this should be an isometry, right? Changing psi or not? No, it's not an isometry.
So the idea is going to be that if you set psi equals 0, and then choose anything for rho and anything for, if you set psi equals 0 and you choose anything for rho and anything for phi tilde, then that's going to be a geodesic.
Okay.
And so it's going to have very low energy for this Hamiltonian just because it doesn't, you don't have any kinetic energy and you have no potential energy. And then you can do other things, but all the things will involve some sort of oscillation.
Okay. So this is like a psi equal to 0 is the pole or the equator?
It's the pole. Well, sorry, no, for SD minus 1 is the equator, but it's also where this SD minus 3 shrinks to 0.
Yeah.
Of this
Okay.
sign.
Yeah. Okay.
So in some sense, it's sort of like you're spinning very fast, so you get pushed to the equator.
Exactly. Yeah.
And then when you do this expansion, so you set psi to 0, so we forget about psi, and we also forget about SD minus 3 because it's now shrunk to 0 at psi equals 0. So altogether, you should think, one way to think about this is like the degrees of freedom given by this SD minus 3 and psi, they just form degrees of freedom of isotropic harmonic oscillator, which you're just putting into the ground state. So you're killing all these degrees of freedom at the same time. And then you expand, you only have rho dot and phi tilde left. And you get this expansion to the second order. So funny thing which happens is that you get this combination 2 rho everywhere. But other than that, you get pretty much standard kinetic terms. So there's some effective mass, which happens to be m/4 for some reason, divided by 2. Then you have this 2 rho dot squared. And then you have phi dot squared times 2 rho. And you also have this linear in velocity term, which came from this cross term. And the interpretation for this is that, when you have terms which are linear in velocity, it's kind of like a magnetic field. well, we didn't have any magnetic field to begin with, but we went into this sort of rotating reference frame where we made things rotate. So this term is describing basically Coriolis force, but we can think about it as an effective magnetic field. And then one thing that you can notice is that you have this funny hyperbolic sine squared of rho here. And if you just treat this as a metric, so you treat that you have some new coordinate twice rho, coordinate phi tilde, and there is an non-trivial metric which multiplies phi tilde. Then you can notice that if you treat this as a vector potential, and you compute the corresponding field strength, so just take the differential of this, you're getting just the volume form for this metric. So really what this Lagrangian is describing is non-relativistic particle in hyperbolic plane, where the radial distance is now twice rho, in a kind of uniform magnetic field, in a magnetic field which is invariant under the hyperbolic isometries. So in this approximation, what the particle does is basically behaves as if it's moving in a magnetic field in hyperbolic plane, and this magnetic field is invariant under these hyperbolic isometries. So that's basically what happens if you try to understand the lowest energy state for a particle.
Yeah, so why exactly are you considering this particle in ADS? I mean, what is the connection with the light cone bootstrap?
So sorry, I was rushing a little bit at this point. I want to understand this problem, right? So I want to diagonalize some Hamiltonian. First, I'm describing the Hilbert space in which this Hamiltonian is going to act. I first gave a formal explanation of what this Hilbert space is, although it was very brief. To describe the Hilbert space of n-particle states, you can describe them in terms of functions which can be defined in this way. And if you go through some conformal symmetry arguments, you find that they basically can be expressed in terms of some polynomials of some auxiliary variables alpha. And that's a true result, and it's mathematically true. There is no approximations that I made anywhere. I just literally studied this quantum field theory that I promised to study, and I just gave a description of its n-particle states. Because as I said, I'm just going to treat this as a perturbation theory in G, so I start with a free theory, and there I can explain everything. And so I have this nice description, but I have now this nice description without any intuition for what this psi is, or what are these variables alpha. And so what I'm doing now is I'm trying to give an alternative derivation for what you should expect the Hilbert space to be. So I'm going to arrive at the same result in a non-rigorous way, but which will have a bit more physical intuition behind it. And the way I do it is I first try to understand the one particle states arranged by twist. And I'm starting with classical action for a particle in ADS, for just a scalar particle. And I'm doing kind of an expansion at low energies in this finite coordinates, which low energies in this finite coordinates means twist. And so I'm just getting some kind of effective theory, which I'm now going to quantize. And I'm going to get the same Hilbert space. Of course, it's not rigorous that I shouldn't have expected to get the same Hilbert space, but I do. And this also kind of what I wanted to do. Like it is the physical setup that I want to study. Low twist particles and just quantizing them from this kind of scratch here. And it just gives me more physical intuition of what this Hilbert space is describing. But separate from this, I also have this rigorous derivation just from the field theory, which doesn't provide this intuition.
First of all, here you have a single, you have a particle for a single field, but your previous model had two fields.
Yeah, but I'm asking so far I'm only trying to describe the states which have n particles of the kind phi. So not 0 sigma particles and n phi particles.
I see.
So what I'm just saying is, if you, the conclusion of this little section is that if you have if you put the particle, classical particle in ADS, and you try to understand classically kind of the types of motion which have the lowest twist, so you have the lowest value of the Hamiltonian, which corresponds to this twist after I quantize, then these types of motions are behaving like they effectively happen in 2 dimensions, parameterized by rho and phi tilde, because this psi variable is frozen at 0 by this discussion. You're kind of spinning very fast in some sense. And effectively, there is a kind of a magnetic field also. So one way of interpreting this is that in this picture, in the original coordinates, there are geodesics which just look like spirals. And after I go into this rotating reference frame, when I have phi tilde, sorry, I'm terrible drawing. So after I go to rotating reference frame where my coordinate is phi tilde, this geodesic
Becomes a circle.
It becomes just a straight line because I'm rotating now together with it. However, if I what happens if I perturb the geodesic slightly? Well, in ADS everything is 2 pi periodic, so whatever perturbation happens, it's kind of going to oscillate around my geodesic. And so the small perturbation after I go into this rotation frame is actually going to look like, if it's small, it's going to look like a circle. Like it's going to look like a small spiral going around my geodesic. And I can ask, what is the effective kind of theory which describes this perturbation? And the answer is that it's the same as if you just had a 2-dimensional particle in a magnetic field in hyperbolic space. And the claim would be that when you have n particles, what's going to happen is that they're approximately all going to sit still, but then you're going to have these perturbations for each of them.
And then how are you going to bring in sigma?
Sigma will just mediate interactions. So sigma will create this pair potential between these particles. So I'm going to integrate sigma out basically and exchange it for an effective, kind of effective non-local interaction for pi's.
Sorry, to begin with, the degeneracy is explained by Landau levels in this magnetic field.
Yeah.
Okay.
So, well, the point is that we want the lowest, like in this whole story, I'm trying to get to the lowest energy thing, so the lowest twist. So I need to look at lowest Landau levels. And so if I'm looking at one particle, I need to look at its states in the lowest Landau level. And then if I have n particles, I need to put each of the particles in the lowest Landau level. And then that I can do in many different ways, and these many different ways explain the degeneracy. If I go to the second Landau level, then that's not going to be the lowest twist state anymore. In fact, I can do this exercise here more carefully and see what is the gap to the next Landau level. And in terms of twist, the gap is 2, which is what you would expect from just kind of CFT perspective. And the same goes for this psi. You can calculate what is the excitation in terms of psi. If you let psi oscillate, then you also get the gap, which is like 2. But if you really want the lowest twist states, then this is indeed the lowest Landau level for this kind of effective problem. And it's well known that the wave functions for lowest Landau level can be described by polynomials in a complex variable in your space, in your configuration space. to this alpha that we had here, which in this construction appeared more or less out of nowhere, in this interpretation becomes the kind of this center of the lowest Landau level inside of the hyperbolic plane, where you think of hyperbolic plane as being realized in the unit disk of the Poincare model. The nice feature of this explanation is that it also tells you what to expect from the dynamics as you add interactions. Because one thing you could be worried when you have three particles is that you might understand, let's say, the effective interaction between these particles when they're far apart. And then you try to apply this effective interaction to their dynamics. And then you might be worried that no matter how you start, maybe there is a situation in which these three particles will eventually get close to each other and your approximation will break. But this actually tells you that this doesn't happen, because no matter whether two kind of lowest Landau levels repel or attract, they don't approach. So if you have, for example, an attractive interaction between two Landau levels, they get attracted, they actually don't start moving towards each other. They start moving perpendicular to the force vector. Because lowest Landau level is like an electron, well, a particle moving in an orbit, and you know that when it's a kind of famous exercise that if you have an electromagnetic field and then you add an electric field, say in this direction, then the electron just starts kind of drifting perpendicular to it instead of following it. And in fact, if you kind of write Hamiltonian for effective Hamiltonian for lowest Landau levels, the effective Hamiltonian is just equal to the sum of pair interactions. There is no kinetic term. So if you have repulsive interactions, you can rigorously prove that they will just not ever come close to each other, because that would make their interaction too large and the sum of interactions have to be conserved.
I have a naive question, like when you have this bare phi dot phi tilde dot term, shouldn't it be contracted with something? Because, I mean, otherwise, how is a Lagrangian a scalar?
Sorry, which term?
No, this magnetic term that you have, phi tilde dot. Sine square, sine sin square, phi sin square, rho phi tilde dot. So
sorry, it's probably I'm making so phi here is an angle, so it's not the field.
Yeah, I understand, but
yeah,
sort of
so it's just written out in components. So are you asking how it's a scalar? It's not really a scalar. It's are you asking how it's invariant?
It's a coordinate. I understand it's a coordinate, but I mean, shouldn't it be contracted with something? Because otherwise,
it's like this.
Yeah.
Right, and you might be worried that whatever I'm telling this K mu is, it seems like that I have some arbitrary direction picked out. So it does indeed like look a little bit non-covariant, but the point is that it's you don't really care about A mu, you only care about the magnetic field, which is D of A mu, and this is actually covariant, it's just the volume form.
Yeah, go ahead, Petr. I think we should let the speaker finish. Already getting a bit late, losing audience.
Yeah. Anyway, so you have this, and then I'm going to go a bit quicker. Then you can get an effective interaction. So we have this interaction Lagrangian, and we can get an effective interaction basically integrating out sigma. It's a Gaussian integral, so we're going to get some non-local potential for phi, and then you can compute its matrix of elements. And then there is between different states. And here, like from this point on, I'm back into this kind of completely rigorous field theory discussion where I'm not using this story anymore. I'm just keeping in the back of my mind to kind of understand what I expect to happen, but these calculations are kind of without any approximations. So I can compute the matrix elements with this interaction Hamiltonian, and it is kind of an annoying calculation, but once you go through it, and I'm not going to do it here, what you get is that in terms of this polynomials of alphas, this effective interaction is very simple. You have, you expectedly have some measure, and this measure is such that if you didn't have this factor here, then this would be just the inner product of these Hamiltonians that you should use, sorry, for these polynomials that you should use. And then the role of inserting the interaction Hamiltonian here, interaction potential, is to insert sum over pairs of ij, so of some function v alpha I, alpha j, which is a kind of PSL2 invariant. So PSL2 is the isometries of our hyperbolic plane. Some invariant Hamiltonian pair interaction, which decays at large distances as you expect. And in this model, so in interpreting these wave functions as wave functions of the lowest Landau levels, what this becomes is that our original problem at leading twist with n phi fields in any ADS and at leading order in G, so this problem is exactly equivalent to just n lowest Landau levels in hyperbolic plane with some pair interaction, which is given by this function v, which you can compute. It's a messy expression, but it's just some nice smooth decaying at large distances potential, which is invariant under the isometries of the hyperbolic plane. And kind of a thing that one might jump at here is that this problem actually has a special name. It's called fractional quantum Hall effect. When you have a bunch of particles in lowest Landau level with pair interactions, people love to study this. However, it is that if you take the kind of the number of particles and spin large at the same time with particular scaling, then it will be literally the fractional quantum Hall effect. That's not exactly what we want to do. You want to keep the number of particles fixed, like say 3 particles, and study large spin when the particles are well separated. But it still is an interesting observation, and probably it's possible that there is some connection to be made in the context of large charge bootstrap, but I'll probably not comment on this. Instead, so while this is an interesting connection, I think the main point is that really important part is when you look at a lot of twist states, you dramatically reduce the phase space dimension. So you get, for example, you get rid of this extra angled psi and other directions on the sphere, and you also were able to see that you don't just have a particle in the plane, you have a particle in the lowest Landau level in the plane, which actually use 2 dimensions of the phase space per particle. And this actually has an interesting consequence, which was not expected, which I did not expect at all, which is that if you look at the leading twist for 3 particles, then this problem is just classically integrable. Because in that case, you have 3 lowest Landau levels in this hyperbolic plane, which means you have a 6-dimensional phase space. So why do you have 6-dimensional phase space? 6-dimensional phase space is because when you have 1 particle in a plane, its phase space is 4-dimensional. But then when you put it in its lowest Landau level, you kill 2 of the phase space dimensions. You basically solve for 1 harmonic oscillator. So you get 2 phase space dimensions per particle. So for 3 particles, you get 6 phase space dimensions. Now we still have this PSL2 invariance of the hyperbolic plane. So we have some symmetries to work with. And if you do Hamiltonian reduction with respect to the symmetry, you reduce the phase space dimension by 4. And the reason for this is that the dimension of SL2R is 3, but it's a phase space, you cannot reduce it by 3. So if you do the things properly, it turns out you can actually reduce the phase space dimension by 4. And so you're left with 2 phase space dimensions. And of course, you still have your Hamiltonian. So if you use conservation of energy, you reduce by 1 more dimension, and then you get 2 one-dimensional trajectories. And so there is nothing chaotic which can happen to 3-body problem in these very special configurations, near these very special trajectories, which are at the lowest twist in this language. And in fact, you can sort of, this is not very scientific probably, but you can see this in just numerical, sorry. Yeah.
No, I was just going to say that if n equal to 3 is integrable, then wouldn't you expect it's integrable for all n? Because it's pairwise after all.
Sorry?
If n equal to 3 is integrable, wouldn't you expect that it is integrable for all n? Because it is pairwise after all. So this is what I was thinking. That
No,
this is what is giving us Yang-Bach
I mean here integrability in a very silly way where it's just you have so many integrals of motion that once you fix them, you're only left with one-dimensional subspaces of the phase space. And of course, if your phase space is higher dimensional, then that's not going to work. Like with 4 particles, you're going to have a 8-dimensional phase space, and by the time you get here, you're going to get 3-dimensional spaces in which your trajectories can have non-trivial shape.
Well, it's pairwise though, right? I mean, it may not, counting may not work in the same way, but
well, the 3-body problem, the 3-body problem in like flat space with Newton interaction is also pairwise, and the 2-body is integrable, but the 3-body is not, right? So it's
no, I was saying 3 being integrable at a 3-body level is a suggestive of higher body integrability, not.
I don't think in this case this is true.
Okay.
I think it's a bit artificial. Like maybe integrability is too loud word, but it's very constrained. Let's put it this way.
Okay.
So, and you can see this in the spectrum. I mean, it's not very scientific, but if you just, one thing you can do is you can, for every spin, you have a fine dimensional space, so you can take some pair interaction and diagonalize it, and you get a spectrum which looks sort of like this. So this is for repulsive interaction. So you have some, the ground state energy kind of gets lower and lower as you go to large spin, because particles get further and further apart, so they can interact weaker. And the structure is quite regular in the sense that, if you look at the spectrum at a given spin, it's just nothing interesting has happened inside of the spectrum in some sense. And as I'm saying, this is not very scientific. So this is literally for this problem, this picture that we have been discussing. I also have another picture, which is for slightly different situation when you have actually kind of triple twist operators in Wilson-Fisher theory of type 2 scalars and 1 scalar squared, which is exactly the situation as this Regge trajectories which I was showing in the beginning. And there it also looks very regular. The given spin, it just has 2 parts now, which has to do with the fact that this is not 3 identical things. But other than that, nothing surprising. But if you go to, say, 4 particles in this problem that we've been discussing, then it starts having much more structure. There are some kind of different bands which start forming. You can see that the density kind of changes in different places. And I mean, it's not, as I said, it's not very scientific method of just staring at these pictures, but it is true that you can see that the complexity is higher qualitatively in 4-body case. But my main point is that actually you can use this observation to understand something interesting about this 3-body case, which is that you can see how this integrability in some sense translates into quantum situation. And it's not really integrable in quantum sense because in the classical physics, in some way, all one-dimensional one-particle problems are integrable, because if you look at the phase space, you just set energy equals constant, and then you see what is the trajectory in the phase space. But of course, in the quantum mechanics, you still have Schrödinger equations to solve. But it's an easier problem than high-dimensional Schrödinger problems. And a similar situation happens here. So for three-body problem, you have a wave function, which is this polynomial of three alphas, and has these properties that, it's homogeneous and shift invariant. And if you think about what this means, it really means that psi is not a function of some three variables. It's really a section of the line bundle on CP1, because you're modding out by some rescalings and you're getting rid of one of the variables by translations. So it really becomes a complex projective plane. And so it's a projective line. So it's complex one-dimensional. So you see immediately this kind of two-dimensional phase space. And your Hamiltonian is originally a function of this three alphas. And technically what you call this Hamiltonian is a Toeplitz operator. But in the end, if you choose nice coordinates in the CP1 and reduce your Hamiltonian to a function of this coordinate, then one thing that you can do is to choose this coordinate z, so that z equals 0 is the minimum of the Hamiltonian. And then you can expand around this minimum near z equals 1. You get some constant plus terms z times z bar. This actually is essentially a harmonic oscillator. And so it allows you to understand the spectrum of this three-body problem near the lowest energy state. So we can understand using this language, for example, the spacing and the ground state energy in this region of the plot. As you go to the right large J, you just separate from, say, light cone bootstrap, which would allow you to understand the spectrum along this individual trajectories. And kind of conveniently, this lowest energy states are just kind of through this procedure, you find that they're, as you would expect, just evenly spaced particles at 2π/3 angle away from each other, just spinning around. And then when you compute excited states, then they're going to do some sort of oscillations on top of that. So sorry for going over time. That's
sorry, Petr. I should have asked like this earlier. With three particles, you can talk about J1 and J2, right? But you just talk about J. So you probably have some particular thing in mind.
With three particles, you can talk about J1 and J2, but there's J1 and J2, they kind of are derivatives which you put in specific operators. But the total spin is just one quantum number. So what happens is that at given value of spin, you have many states, and the degeneracy grows linearly in three particle case.
And this J is just the total spin, I guess. Yeah. Okay.
Yeah. All right. So, kind of the summary of all this is that I think we can understand. My main point is that if you arrange the states, even like I at first thought that the three-body problem is hopeless from this point of view, but actually kind of trivial reasons in some sense. If you arrange this three-body problem by twist in ADS, then it can be understood because the phase space is very reduced. And this is kind of a quantum thing. Of course, if you have corrections which are so large that they start mixing these different twists, then it becomes really complicated. And there are, of course, regimes in which this three-body problem is very hard to solve in the same sense as it's hard to solve in the flat space. But there are also other regions where you can solve them. You can solve it for a given Hamiltonian, for a given interaction, and there are parts of spectrum that you can analyze using this methods which are separate from the parts that you can analyze using the kind of double twist, as long as you know the effective Hamiltonian. But also this effective Hamiltonian, you can hope to be able to understand it for a given CFT, this effective interaction, as long as your these blocks of excitations are far separated. And very nicely, the regions where we can understand the three-body problem is actually these sort of regions when they're very separated, just in kind of a democratic way. Like in this picture. And so kind of this, I think, is a nice observation, which says that, if you are able to formulate what this effective Hamiltonian is, you can actually do something with it, which is, at least to me, not obvious from the start. So I'll probably end here, and sorry again for going way over time.
Thank you so much, Peter, for a wonderful talk. Yeah, we did have many questions, but there are some remaining questions. So one question, yeah, go ahead.
Go ahead. So I don't still understand the relationship between the field theory model and the quantum mechanical model that you wrote down. So, for instance, the quantum mechanical model had only one particle, and
I started with one particle, yes.
Yeah, and so.
But then we take several particles. So
yeah, you take
we
several
take tensor
particles,
product
but
of
in
this
order for them to
space.
interact, you have to add something else to the Lagrangian, right? The particle Lagrangian.
He did that with the V. The V
Yeah,
alpha 1, alpha 2.
Yeah,
No.
this quantum mechanical discussion.
Magnetic field is part of the it's part of the single particle Lagrangian, right?
Yes, magnetic field is the part of single particle Lagrangian, but the logic was so V that was referred to is probably this V, which is not part of the single particle Lagrangian. The logic was that I have a field theory model which I want to, in which I'm interested in diagonalizing a certain Hamiltonian, the twist Hamiltonian. And I can diagonalize it in free theory. And I know the spectrum in free theory, and the spectrum is highly degenerate. So what I'm interested in is how this degeneracy splits when I add perturbations, this particular perturbation here. Now, to understand that, I first need to understand the degenerate subspace that I want to split. And I had two ways of understanding this degenerate subspace. One was formal and kind of rigorous, which is to go through the wave functions of this field theory model and just write them down in free case. And another was to kind of give a more physical interpretation to these wave functions by going through this single particle exercise, where we see that kind of this problem is similar for a single particle. This problem is similar to a motion magnetic field in hyperbolic plane for one particle. Then for n particles, this is n particles moving in magnetic field in hyperbolic plane, and their Hilbert space for this n particles is the same as the Hilbert space in which I want to split, which is the one that I want to analyze from the field theory point of view. Now, the interaction, I'm not adding it by hand here. I'm not trying to come up with interaction for this n classical particles or n quantized particles. The interaction I already have. It's this Lagrangian for the field theory model, and it tells me what this V is. And then once I do the calculation, non-S calculation, and I'm not thinking about these classical particles, I'm just doing a field theory calculation and computing the matrix elements, I can write this matrix elements in terms of this wave functions that I have, which again, I also obtain these wave functions directly from a field theory calculation. But then if I go back and interpret this wave function as actually coming from this situation, then in this language, it becomes as n particles in lowest Landau level, now with pair interaction in H2. But this pair interaction, I didn't just choose it, I derived it from this interaction in the field theory. So this whole part from classical.
Okay, so at the particle level, you're not invoking the interactions, but then when you're going to the field theory level, you're adding that term and kind of getting it. Is that right?
Yeah. So here, this particle, kind of classical particle picture and then quantized particle picture, it's just a language to describe this kind of subsector of the field theory model, just to give some physical picture to it.
Can you write down the form of V?
Sorry?
What is V exactly? V alpha 1, alpha 2. Can you write it down?
Well, I can write it in the sense that V is
You say it's PSL2R invariant parent. What does that mean?
it's a messy function of the distance from alpha 1 to alpha 2.
Okay.
So the hyperbolic distance. So the hyperbolic distance is something like alpha 1 minus alpha 2 squared minus alpha 1 squared.
I see. I see.
Alpha
Okay.
2 squared, something like this, and you have to take our cosh of this or something like this. So it's a function of this
I
kind of
see.
ratio. And this, I mean, it's a really complicated function. If you honestly want to translate this into this function, you can. And the answer is contains, as I said earlier here, like this answer for this effective potential basically contains everything that you can learn from Lightcon Bootstrap about this sort of situation. So it contains the entire answer that you get when you apply inversion formula, Lorentz inversion formula to this T-channel block in the dimensions. So it's not.
And is V order G? You're taking the first order, right? It's just the exchange diagram, the leading exchange diagram.
Oh, it's quadratic in G because it's exchange diagram.
Oh, right. Yeah, sorry. It's quadratic there. Okay. I see. And okay, so right. Thank you. Yes.
But hopefully the idea is that you know when you do Lightcon Bootstrap, you kind of interpret this, like the conformal block that you include is just this thing, and you interpret it as a
yeah, I think it's applicable to all orders at large distances, a large G, right?
Yeah. Well, I mean, there is some exponentiation that you expect to happen, well, similar to what you expect.
Yeah, this is what I was wondering about, some sort of iconization, right?
Yeah.
So how would that work for the three-body case? These quantum effects must become classical.
I didn't mean iconization. I meant exponentiation in the sense that, like, you know, when you include the kind of ladder diagrams.
Yeah, that's what I mean by iconization. Yeah.
Well, I mean, here it's understood to some, like in the in kind of double twist case, it's understood to some level that if you include this guy's back into the left hand side, then you're going to see terms which give the anomalous dimension, like which start kind of exponentiating their anomalous dimension. Because it's part of the story, like with the Lorentz inversion formula. It's not like you get, if you apply Lorentz inversion formula to the left hand side, it's not like you get this function C delta J with shifted poles. You only get the function of C delta J with shifted poles to the first order. And then you have just not included things which will give the second order shift and so on.
Right, but that controlling parameter is 1 over J or G?
1 over J, yeah.
So, but these diagrams are about higher orders in G, right?
Yeah, but they also have higher orders in J because each of these things has to propagate distance log J.
Okay,
which is also
I see.
A similar thing applies to like if you imagine that I know sigma had a cubic interaction that would produce at leading order, say the three particle interaction. This thing has like, you know, imagine each of these things is far away from the kind of ADS center. And then this has like 3 long pieces here compared to like 2 long pieces it would have in 2 particle interaction. So it's I think if you say try to imagine higher particle interactions mediated by the same sigma, then they will actually be more suppressed than 1 over j.
No, just to understand this by this two particles thing. In the two particle thing, this diagram, ladder diagram, I see that it is a higher order in G, but you're saying it's also higher order in log J. Is that what you're saying?
Yeah.
Log J. But as far as the power of J is concerned, it's the same, right?
No, sorry, I meant higher power in J, because each of these things comes as an inverse power of J. I think that's the correct interpretation, because you have these two particles and they're far apart, and you need to propagate from one to the other, and effectively, no matter what propagates, whether it's graviton or whatever. It's,
I see. The distance is log J, so e to the power minus mr. So that's like J to some power minus m. I see. And
but the important point is that it's not like, one comment is just that it's not just mr. It's like the graviton, for example, would also decay exponentially, because ADS is just ADS.
Okay. Right. Also, so is there a way to directly see that the J expansion just agrees with the G expansion?
That's a good question. So I don't have a very good clean way of saying this, but I just want, in some sense, it's like an open problem to have a convincing, effective theory, I guess, for this large spin.
Okay, that would help you argue these things for higher particles clearly, I guess.
Yeah.
Okay.
So there is this dream of having kind of large J effective field theory, I guess.
I see.
So it's not really understood how to do that.
Well, thanks so much, Petr, for being so patient with all the questions. All right.
Thanks a lot.
Bye.
Thank you. Bye-bye.